what we're about to derive only applies in a very limited subset of circumstances. But since the circumstances show up now and then, it's useful to not have to rederive them every time. We're in fact assuming a coordinate system where x is horizontal to the Earth, y is perpendicular, and we're assuming that we have a projectile that starts at the origin and is launched with some initial speed v0 at an angle alpha naught from the horizontal. Our initial point in time is then the launch time, and then we're looking for an arbitrary later point in time, t. In our first dimension, our initial x position is equal to 0, and our final position is unknown. We'll call that x. Our initial x component of the velocity is our initial speed, v0 cosine alpha naught. We don't need the 0 in there. And our final x component of the velocity is equal to v0 cosine alpha naught, and that is because there is no acceleration in the x dimension. And so we're going to say that our initial time is equal to 0, and our final time is then equal to some generic time t. This tells us that delta t is just t. So now, if we look in the y dimension, our initial y is 0. Our final y is unknown, so that's just y. Our initial y velocity is equal to v0 sine alpha naught, and our final y velocity is unknown, so I'll just call that v sub y. Our acceleration in the y is towards the center of the Earth, so that's a negative g, and our initial time is 0, and our final time we'll call t. What else can we say about this system? Initially, our speed is just the sums of initial x plus initial y, but we can also relate then our angle, tangent of alpha naught, is equal to the initial y over initial x. We also know that at the final time, we have our final speed is the square root of vx squared plus vy squared, where vx squared is the same as the initial. And then, if our final velocity makes some angle alpha, that is equal to the final y component over the final x component of the velocity. So now let's use this for our kinematic equations and see what we come up with. In the x dimension, it's uniform motion. There's no acceleration. X at some later time is equal to the velocity in the x direction times the time interval, which in this case is just t. Now in the y dimension, our final y is equal to the initial y, which is 0, plus the y component of the initial velocity, which is v0 sine of alpha naught times time, minus 1/2 g t squared. And we also know that the final vy is equal to the initial v0 sine alpha naught plus the acceleration times the time interval, which is minus gt. If we solve this for time, time is x over v0 cosine alpha naught, and then I'll substitute this into here for time. So this gives us y is equal to v0 sine alpha naught times the time, which is x over v0 cosine alpha naught, minus 1/2 g, and then this thing squared, x over v0 cosine alpha naught squared. If we go ahead, simplify this, v0's cancel, this turns into tangent. We have an expression that relates our y component of the position to our x component of position. Y is equal to tangent theta naught x minus g 2 v0 squared cosine squared alpha naught x squared. And so this is the parabolic motion. The y is a function of x. These are constants, and so you have a linear term in x minus a quadratic term in x. This might simplify some of the calculation. The key being you always have to remember your assumptions.